I'm one of the co-editors-in-chief. The other one is Professor Wenping Hu from Tianjin University. Today, Professor Meilin Liu is a speaker. Before his talk, let me briefly introduce Professor Liu. Professor Liu is a Meilin Court Chair, a Reagan's Professor, and the Associate Chair of MSc at Georgia Tech. He received his master and PhD degrees in MSc from UC Berkeley. Professor Liu is a world-leading scientist in the area of materials for electrochemical energy storage and conversion. He is a fellow of the Electrochemical Society and the American Ceramic Society. He has also received numerous honors and awards. Today, he is going to talk about recent advances in reversible fuel cells. Let's welcome Professor Liu to give a talk. Professor Liu, please.
Thank you very much for your kind introduction. And also, I would like to take this opportunity to thank Professor Zicheng Zhang for the invitation and for this opportunity to share some of our recent research project with everyone. Let me see, I'm trying to open up the file. Can you see my slides? Is everything okay? All right. Okay, so I'm going to introduce some of the recent fuel cells. So I'm going to start with a very brief introduction to the motivations and some of the critical challenges we are facing. And then it's going to talk about the objectives of our research and followed by the scientific approach. And basically, we try to design the hetero-interfaces and also using in situ and operando experimental techniques to probe the surface and the interface of electrochemical systems. In particular, I'm going to try to give you some update in two directions. One is the development of catalyst for oxygen reduction reaction and for oxygen evaluation reactions. And the second aspect will be the catalyst for hydrocarbon fuels. And then we're going to conclude with a brief summary. As we all know, the demand for clean and secure energy is one of the urgent challenge we are facing today. As we know, we can no longer just keep burning the fossil fuel to meet our energy need. The only viable option is going to be the renewable energies, such as solar, wind, and geothermal energies. However, in order to make use of renewable energies, and the key challenge is how to store the energy in a safe and cost-effective manner. The existing energy storage technologies are inadequate and also very expensive. So what we're facing today is we have to develop a new generation of low-cost, highly efficient energy storage and conversion systems that can be integrated with a lot of renewable energy sources. As of today, we're still heavily relying on fossil fuel. For instance, about 80% of electricity is come from fossil fuel. Now, if we can use the advanced electrochemical energy systems such as fuel cells, batteries, supercapacitors, then we can immediately increase the energy efficiency and reduce the pollutant emission by almost 50%. Also, if we can make use of the renewable energy sources, We can use batteries, supercapacitors for storage, for small-scale applications. But for large-scale energy storage, batteries and supercapacitors are inadequate, and we have to rely on fuel cells. So that comes to the challenge, what I'm going to talk about today. And what we hope for is that we're going to using the renewable energy such as wind, solar, and geothermal energy, and use those electricity to produce renewable fuel. And then when electricity is needed, we can run the fuel cell in the other direction to convert the chemical fuel into electricity. So that is the so-called reversible solid oxide cell. And that's what I'm going to focus today. So this is the schematics for a solid oxide fuel cell that can be powered by methane or natural gas. So this concept was developed under a ARPA-E program. And so in this sketch here, one of the key components is the anode. The anode must be multifunctional, especially if you're going to use natural gas or methane to power the fuel cell, then the anode here must have the ability first to do reforming of the hydrocarbon fuel to hydrogen, and that process is critical. Otherwise, your anode will be quickly deactivated because of coking. So the multifunctional anode here will typically consist of 3 layers. One layer is for reforming up front, then the next will be a layer for water gas shift reaction to convert CO to CO2 and produce additional hydrogen. And then when you come to the interface between the anode and the electrolyte, that's where the hydrogen is electrochemically oxidized. Yeah? The key challenge is how to design a multifunctional anode that will be able to handle methane or natural gas without other reformer or a separate reformer. Now, this has been done at high temperatures, but the key challenge is, can we successfully make use of methane or natural gas at a temperature below 500 degrees C? Department of Energy CCAR program has been running since the year 2000, so it's for almost 20 years. Their objective is to develop affordable fuel cell systems. One of the major objectives is to convert coal gas directly into electricity and to maintain efficiency up to 60%, and with 99% of CO2 capturing. So those are the major objectives. And ultimately, the Department of Energy is expected to using solid oxide fuel cells at the center here to be integrated with the gas turbine, and that combination will produce the highest energy efficiency. So this is envisioned as the future technology for power generation or for electricity generation. And the implementation of this technology will have the potential to dramatically increase not only energy efficiency, but also reducing the pollutant emission. Now, another part of DOE, that is the Office of EERE, that stands for the energy efficiency and renewable energy. They are interested in the reversible solid oxide cells for producing of chemical fuels. For instance, in this schematics here, you can convert CO2 directly into syngas, and that syngas can be further processed into syn fuels or many other different cleaner fuels. So the electrolysis of water and the CO2 use fuels that are running in the reversible direction. And that is another new direction for the ERE. So there you envision the reversible solid oxide cells have the potential to be the most efficient and low-cost option for energy storage. So here we're talking about large-scale energy storage to be integrated with smart grid. This is the schematics here. We're using a proton conductor-based system. Now imagine if there is excess electricity from renewable energy like solar, wind, geothermal, then we can use that electricity to produce hydrogen by electrolysis of water here. And then when there's need for electricity, and we can run this hydrogen through the fuel cell, produce electricity. So this is the so-called reversible solid oxide cell. And currently we have demonstrated the round trip efficiency is about 70%. So that means from the electrolysis of water to production of hydrogen, and then from hydrogen back to electricity. From electricity to electricity, and the round trip efficiency is about 70% at a current density of 1 amp per square centimeter. So this has been demonstrated at a temperature somewhere about 600 to 700 degrees C. So this is envisioned to be one of the most efficient system for large-scale energy storage and conversion. So in this graph here, as we all know, hydrogen is one of the cleanest energy carrier. So we can use the solid oxide cell running in the electrolysis mode to convert electricity from renewable sources to hydrogen. And then this hydrogen, of course, can be used for many different applications, as you can see here, from transportation to many industrial processes. And then if there is need for electricity, we can also use fuel cell to convert hydrogen back into electricity and feed that electricity to the power grid. So this is the hydrogen economy, but at the center of this hydrogen economy is the reversible fuel cell processes. And so for that particular case, integrate with the power grid for large-scale energy storage. And that will be an important component for interfacing of renewable power and the conventional power. And also Nissan has demonstrated solid oxide fuel cells can be used to power electrical vehicles. So this is actually, they're using biofuel to power a minivan. So the advantage of solid oxide cells, including high efficiency, from chemical to electrical, the direct efficiency is about 50%. Now, if you combine with turbine, make use of the thermal energy, the efficiency can be up to 80%. And for the reversible operation, 70% of round trip efficiency has been demonstrated. And also, of course, have the flexibility. You can use many different fuels, and you can have different size, modality, dispute generation, durability, etc. So those are the unique advantage of solid oxide cells. However, there are a few challenges. The reason these kind of systems has not been widely implemented is because of some of these challenges. For instance, when the cell is operating in the reversible mode for electrolysis, the Faraday efficiency relatively low, and that's one of the things we have to improve. Another challenge is that the performance of the anode is inadequate. That represent one of the major energy loss in fuel cell systems, especially when the temperature is relatively low. One of the reasons we want to reduce the operating temperature, because at lower temperature, we can use much less expensive materials for cell component. But then the performance will decrease as the temperature is reduced. So one of the challenges, how can we enhance the performance as the operating temperature is reduced? And finally, degradation of electrolyte-electrode interfaces, especially when it is exposed to water. Now, for the reversible operation, especially for electrolysis of water, the water content can be very high. A lot of the conventional materials will have stability issue when they're exposed to high concentration of water, to hydrocarbon fuels, and to carbon dioxide. And more importantly, is to some of the contaminants. When we have a fuel cell stack, inevitably there are impurities from sealant, and there's chromium from interconnect materials, and contaminants from ambient air, and also sulfur containing species if you are involved in any hydrocarbon fuel, and the coking. So for the anode here, especially if we're talking about using natural gas to power fuel cell, the contamination from the contaminants within the natural gas could be one of the major challenges. Yeah. So from a scientific point of view, and here is our challenge. The question is, how can we rationally design surface and the interface of this kind of systems? Because we know surface and the interface is right at the center of all chemical and energy transformation processes. And so the performance of all these devices is actually determined by the rate of charge and mass transport along surfaces, across interface, and through porous systems. And so that's why the interface is extremely important. Another reason is that when we're talking about durability, we want the fuel cell system run for at least 5 years or even for 10 years. But the degradation often initiate at the surface and the interface. So unless we have a good control of surface and the interface, we will not be able to get the performance, neither the durability we're looking for. So next, I'm going to briefly overview some of the progress we have made along two directions. The first one is the development of catalytically active and durable catalyst for oxygen reduction reaction and oxygen evolution reaction. So that is the catalyst we use for the air electrode. The air electrode, the oxygen involved electrochemical processes is relatively slow, and the overpotential represent significant energy loss in these fuel cell systems. The second aspect I'm going to talk about is the catalyst for fuel electrode, and especially for efficient utilization of hydrocarbon fuels, then the anode is the critical part. And how can we mitigate some of the challenges we're facing with hydrocarbon fuels? So that's the second aspect. Now, first, let's look at the air electrode. For the air electrode, when we operate fuel cell to convert chemical fuel into electricity, here what we have is that the molecular oxygen come in to the cathode and first get absorbed, dissociate, and then reduced, eventually disappear in the lattice. But this process is very sluggish, especially at lower temperatures. And so there's a lot of fundamental study has been done, try to follow the elementary steps to understand the mechanism and try to rationally design a better surface. the key challenge is that how can we accelerate these processes at a temperature below 500 degrees C, or for the intermediate temperature fuel cells. Now, as we know, a lot of different materials has been studied, including many different types of complex metal oxide. Yeah. In particular, at the center is the perovskite. Perovskite is a very flexible structure material. It's open structure, give us a lot of flexibility. You can modify the chemistry, the structure, and therefore the catalytical property. For instance, you can control the surface by purposely control the cation segregation processes. In some of cases, you can create a surface catalytic active coating, or in other cases, you can have absolute of some of the cations within the structure and get reduced and produce nanoparticles of metals under reducing conditions. So by carefully controlled process and conditions, you can create a surface with nanoparticles with high catalytic activity. So another direction is that we want to create heterostructured electrode. That is the heterojunctions. And by hetero, then it means you have two different materials. At least they either have difference in composition or difference in structure. And therefore, at the interface, that's where you're going to create electrochemically hot spot. Yeah? So here, just schematically illustrate, you can introduce a catalyst by infiltration, and that will interact with the parent oxide and then create heterojunctions. Or by changing the process and condition, you can have exsolution or precipitation of cations from the parent phase and create nanoparticles on the surface. Either way, this will create the so-called heterostructure or heterostructured electrode. And it is the junctures between two different materials. That's where often you can have a uniquely designed catalytical property for the chemical and energy transformation process. Now, for fundamental study, typically we can use different ways to create a structure. For instance, by create multi-layer, you can use PLD, ALD, and with atomic precision to put down different layers of atoms and create a multi-layer and create hetero-interfaces. Or you can have vertically aligned nanocomposites. Yeah? And so those architecture or configuration will give us ability to create hetero-interfaces, and then by carefully control the chemistry and the structure, and you can get the hetero-interface. Now, another simpler way is just using nanoparticles of different materials. You have a mixture when they mix together, and even it is random, but if the particle size is very small, you actually can create a large number of active site for a porous electrode. Yeah. And now, why do we need nano hetero-interfaces? And from a scientific point of view, the reason is that this type of nanostructure is going to significantly enhance catalytic property because it could create a strain across the interface or induce a space charge region. You could have accumulation or depletion of certain charged species or form certain defects at those junctures. Yeah. And it also increased the so-called inherent activity due to interfacial nano-ionic effect. Now, this has been demonstrated in a few of the solid ionic systems by creating the interface of different ionic conductors, and that actually can dramatically enhance, for instance, ionic transport. And also, it greatly increases the number of active sites on the surface of electrode, and therefore it will reduce the resistance to chemical energy transformation. So just by simply increase the surface area, that will also have important effect. And finally, as you reduce the dimension of the particles, you also reduce the solid state diffusion length, and therefore that will enhance the rate capability for many of the processes. So as an example here, this strain created on YZ, for instance, is yttrium stabilized zirconia. And if you grow a thin layer of YZ on different substrate, you can either create compressive strain or tension. Yeah? And as you change the nature of the strain, the ionic conductivity can change quite significantly. This has been demonstrated that you can change the conductivity by order of magnitude. So that is use the lattice strain created at this interface. You can also create different defects, for instance, dislocations. You can change the electronic structure near the junction area, or by create a space charge region. This is accumulation of charge at the interfaces, or by through cation segregation or enrichment that could create unique interfaces. All those are possibilities to enhance performance. So typically we use a model cell. By model cell, that means we have precise control the geometry of the electrode. So often we're going to use like PLD, even molecular beam epitaxy, or ALD, atomic layer deposition. Those give you very precise control of the electrode surface and the interface. And then we can also use the so-called infiltration processes to modify porous electrode. So there's a lot of demonstration that by introduce nanoparticles of different catalysts, you can dramatically enhance performance. So here is, for instance, LSCF, blank electrode. By put down different infiltration, you can significantly enhance performance. Yeah. And we have also used the so-called surface solid gel process to deposit different catalysts on porous electrodes. So this gives us very precise control of the chemistry and morphology of coatings in a random porous structure. Yeah. As a specific example here, we have put a PNM coating on LSM, and then by control the process and condition, you can also have absolute nanoparticles of pyridinium oxide, and that create a uniform coating plus some nanoparticles on the surface. And this is what it looks like under SCM. You can see the nanoparticles after different time of annealing. Then by carefully analyze the chemistry and the composition of the material, we identify it is actually pyridinium nanoparticles on a PM coating. So this is schematics of the model for that structure, surface structure created. And then we use DFT calculation actually try to explain why this coating can increase not only the catalytic activity, but also the stability. So the pyridinium oxide is very active for absorption of oxygen and oxygen reduction. And once the oxygen is incorporated into pyridinium oxide, then it goes through the channels of the PNM, then disappear in the LSCF electrode. Another example is that so here we create nanoparticles that's barium cobaltite nanoparticles on PBCC. Once again, the geometry or the configuration is similar. Basically, the nanoparticles have high catalytic activity, and that enhance the properties. So here just electrochemical measurement in comparison to a bare PBCC electrode, and with the coating or absolute nanoparticles, the resistance dramatically reduced, and also the stability is dramatically increased. Now, another interesting effect we have observed is that now LSCF, that is one of the conventional or the state-of-art cathode materials for solid oxide fuel cells. When you introduce small amount of water vapor into the air, the impedance deteriorates very fast and quite significantly. So that's one of the problems with LSCF degradation. In contrast, the PBCC here, when you introduce some water into air, the impedance actually decreases. So as is clearly shown here, for PBCC, first of all, the impedance is small, but also decrease as you introduce water vapor. And so that really make us try to explain what's happening there. And we're using in situ Raman measurement here and try to probe what are the species on the surface, and as we collect electrochemical measurement. For instance, here, this is the spectrum, Raman spectrum, when the air is dry, and once the water introduced, you see the evolution of Raman spectrum. Now we'll be able to observe a lot of the oxygen species as a function of time and different conditions. So you can not only collect the spectral information about surface chemistry, but also the electrochemical performance of the electrode. So here the impedance decreases as you introduce water into the system. So from dry to wet, the impedance shrink, and we correlate this intensity of different peaks. So that give us the indication, the accumulation of different species on the surface and the interfaces. So we actually come up with a model and try to explain why when in the presence of water, PBCC actually increased the catalytic activity. And we built the model based on experimental results from the Raman measurement, give us what are the species on the surface, and did a DFT calculation ultimately, and this explains why the PBCC give you higher catalytic activity in the presence of water. It mostly is because of the surface absorption of water create an OH group on the surface, and that actually accelerates the absorption of oxygen and make the absorption, dissociation, and a reduction of oxygen occur on the surface more readily. Yeah. So that's for the progress in air electrode. Now next, let me just quickly mention a few things about the second aspect, that is the development of catalysts for fuel electrode. So here, if we're going to use hydrocarbon fuel without a separate reformer, we're going to bring hydrocarbon molecules directly to the anode of solid oxide fuel cell, then there must be a mechanism for removal of carbon, because carbon is going to form on the surface. Unless there's a way you can remove carbon, then coking is going to be the problem. So here's a schematic shows if we have a barium oxide nanoparticles on the surface of a nickel. When carbon atoms form here, because the dissociated absorption water create OH group react with carbon form COH, and the COH dissociated into H and CO, and both H and CO can be oxidized to water and CO2. So that is the way to clean the surface. Yeah? And that occurs at relatively high temperature. Once again, can we sustain this process at a temperature below 500 degrees C? So at 500 degrees C, and that catalyst is inadequate. So here we actually discover another new catalyst, that is the nickel-doped cerium oxide and ruthenium doped, actually co-doped. There is coordination or synergistic effect between two different dopants. So what we have here is that we're using a defect silver oxide as the catalyst. We have nickel and ruthenium doped into the structure. On the surface of the catalyst, so basically we have three things. We have nickel cation, it's not nickel metal, and that is very active for activation of methane. So basically to break the carbon hydrogen bond. Ruthenium cation is active for breaking the oxygen hydrogen bond or dissociate the water molecule. Oxygen vacancy on the surface of silver oxide, that's important for the coordination of these processes that can provide oxygen or take oxygen away for the reforming process. So with that, we designed a catalyst. It is nickel ruthenium co-doped, and that gives us the best effect. So here just showing some results. We have nickel doped, ruthenium doped, and nickel ruthenium co-doped. Basically three cases. Yeah. And the green one is the co-dop. Clearly that gives you better performance. This is another way to look at this turnover frequency here. The red is nickel dop alone. Black is ruthenium dop alone. So both are relatively poor performance. But when we have both together, blue here have co-dop, that's dramatically better. So there is a synergistic effect. If you measure the activation energy, once again, for co-doped catalyst, the active energy is much smaller. And so we assemble a fuel cell, put it into fuel cell, and basically we have one layer of that reforming catalyst up front, and that help us to do the reforming as methane or propane come in, even with only 3% of water. So basically it's nearly dry. And then they're going to, this catalyst promote the reforming reaction, but as reforming occurs, then that produce hydrogen. So the hydrogen will be oxidized in fuel cell. That oxidation produce more water, and the water help to do reforming. So this actually become a circular process. Once it's getting started, and it automatically make use of the water produced by fuel cell, and you no longer need water. So that's why we're able to use almost dry methane to run this fuel cell. Now, when we put the catalyst on the surface of polished electrode, the effect getting more dramatic, and that makes this system become functional at a temperature as low as 500 degrees C or even lower. And you have methane direct feed into the fuel cell and give you a very high performance. So here, for instance, operate a few hundred hours, the performance is pretty steady with nearly dry methane. And so the performance is very unique because of the catalyst. Now, to understand the nature of catalyst, we actually did X-ray absorption spectroscopy and atmospheric pressure XPS and try to analyze the oxidation state of nickel and ruthenium. So the conclusion here is that both nickel and ruthenium are in the oxide form or cations. They're not metals. Yeah, if the metals, actually they're not efficient. And finally, from DFT calculation, that explains how it works. Basically, nickel, as we know, is very active for cracking the methane, so breaking the carbon hydrogen bond. And ruthenium is active for breaking the water. And the together to coordinate, and plus the oxygen vacancy on the surface of silver oxide, the coordination or synergistic effect between these three things, and it becomes very efficient for oxidation of methane in solid oxide fuel cell. So basically, you can run methane or feed methane into the fuel cell and directly convert that to electricity. Now, we also use Raman spectroscopy to study the detailed defect structure of this catalyst. So here, the Raman spectrum is very sensitive to the local configuration. So this first cube here is if you have a perfect silver oxide, okay, you have silver 4+ sitting at the center of the cube, So the 4+ series coordinate with 8 oxygen. That give you a peak here, F2G. That's where you're going to see this strong peak. So that's the strongest peak for silver oxide, zirconium oxide. However, if you have a vacancy here, so this is a 4+ cation coordinated with 7 oxygen. There's one side is empty. That actually is the alpha in this location here. And then if you have a 3+ cation, so when series partially reduced from 4+ to 3+, now the 3+ at the center of Q coordinated with 8 oxygen, that give you the peak on the beta here. So we can use Raman directly to probe how the series oxide change under operating conditions. So this actually gives us mapping of this defect structure of surfaces. Yeah. And also we use the Raman to follow the sulfur poisoning on electric surface. So without moisture here, sulfur actually can have dramatic effect on the electrochemical performance if there is no water. When it's dry, sulfur will accumulate on the surface and cause serious problem, the so-called sulfur poisoning. But if there's small amount of water, so here when we introduce small amount of water, in the presence of water, the resistance drops significantly. Also, as you can see the spectrum here, the sulfur vibration get much weaker. And here's the impedance. So all that also give us the indication how the surface chemistry is related to electrochemical performance. So from the spectrum, that give us the information about what's going on the surfaces. And then with DFT calculation, we'll be able to figure out the mechanism. So that's one of the strategies we're using. So finally, for the reversible fuel cell, this is the performance we have obtained to date, the best performance. So as you can see here, the current density can be as high as almost 2 amps per square centimeter. The OR potential is still relatively small. Yeah. And here is the reversible operation. So that's for the energy storage. If you have daily switching from the electrolysis mode to fuel cell mode back and forth, and see this switching give you very steady performance. And the efficiency, round-trip efficiency is about 70% at 650 degrees C at 1 amp per square centimeter. And this is currently supported by one of the ERE, DOE ERE project. So let me just conclude here. In summary, we have demonstrated hetero-interfaces have potential to dramatically enhance performance and durability of electrode or the electrochemical cells. And then in situ operando characterization are vital to gaining insight into the mechanistic understanding of electrocatalytic processes. So unless we can do those in situ and operando measurement, it would be very difficult to really understand what's going on within the fuel cell system. Surface modification, especially through infiltration, is an effective approach to achieving high performance at a low cost. And finally, we have identified efficient catalysts and methane reforming catalysts and ORR catalysts. All those are functional at a temperature less than 500 degrees C and demonstrate reasonably high performance. Finally, I would like to acknowledge the contributions from postdoc students and collaborators and the support from Department of Energy and several programs and Blue Haven National Lab, Phillips 66, Nissan, etc. Thank you for your attention. I will be more than happy to answer any questions. Thank you.
Hi, Professor Liu. Thanks for your wonderful talk. Now I will host the Q&A session. We have collected some questions from the live platforms for you to answer. Thanks for your time. Yeah.
Sure.
So the first question is, just now you mentioned the nanostructured. So will the defects such as strain and dislocation stable at a high temperature in fuel cell?
Okay, that's a good question. So depends on the material system. Yes, at a high temperature, certain strain will remain, but if the strain is too large, then you're going to get a relaxation. So there will be relaxation, and then that effect will get less and less. But that can relax only to a certain degree. So it depends on material system. I also depend on temperature. The higher the temperature, you can get a more relaxation. And so that's another reason we want to push the operating temperature to lower temperature. So at a lower temperature, then you're going to have more strain effect locked into the system. So if your temperature is sufficiently high, eventually you may lose all this strain effect. That's a very good question there. Yes, so it's going to depend on temperature.
Okay, thank you. And the new question from the audience is, what's the current challenge and the perspective of air electrode based on the materials? Yeah, thank you.
Okay, so as I mentioned here, air electrode, typically, if you look at most of the fuel cell performance, air electrode contribute the most of the energy loss. The interfacial resistance or interfacial polarization mostly come from air electrode. Yeah. The reason is that this oxygen reduction is a very sluggish process, especially when your operating temperature is low. If you below 600, typically below 600, this is going to get more significant. Yeah. So that's one of the main reasons you have to figure out how to accelerate oxygen reduction processes, especially at low temperature. So that's first challenge, how to further reduce resistance. Another challenge is that, especially for reversible fuel cell, now the cathode can be exposed to a lot of water. That depends on which materials you use as electrolyte. Let's see, if you use proton conductor as the electrolyte, then water will be fed to the cathode, to the air electrode. Now, actually, when you do water electrolysis, the air electrode become anode. Yeah? You're going to have water come to the air side. Okay? Then you're going to do electrolysis of water on the air electrode. Then you pull protons through the electrolyte to the other side of the cell. So now you can imagine the water concentration is very high. You need a lot of water. The conventional air electrode materials for solid oxide fuel cells, such as LSM and LCF. LCF actually will deteriorate when small amount of water is introduced. Even a few percent of water coming, LCF is going to show degradation. One of the main reasons is that when water comes to this anode, water absorbs on the surface of LCF that induce cation segregation or cation enrichment. This strontium actually is going to move to the surface, then form strontium oxide. If there is sufficient water, then form a strontium hydroxide. So strontium oxide hydroxide is going to really deteriorate the catalytic property. So that's one of the major problem with LSF and LSM, especially if you have a lot of water. So you have to find a new material that will resist water, especially resist high concentration of water if you're going to have a reversible fuel cell. Okay. Also, in another more critical issue with air electrode is that often the interconnect will have certain content of chromium. Either you're using alloy or ceramic. Chromium is have very high resistance to oxidation. But the chromium, especially when there is water present, chromium is going to get into the gas phase. And then chromium move around through the system. can deposit on the air electrode, and you could form like some of the strontium chromate, yeah, and that perceived on the surface, those are insulating. That's going to deteriorate the degradation. That's typically called the chromium poisoning. So chromium poisoning will become significant, especially when humidity is high. Yeah, so those are the major problems. So first, you have to reduce the polarization resistance. You want to make the air electrode very catalytically active. Number two, you have to have water resistance. Number three has to have resistance to chromium poisoning. Those are the major issues.
Okay, thank you. Thanks for your detailed response. Yeah, another new question is, just now also you mentioned the water absorption on the air electrode. So generally speaking, for water, yeah, if we will introduce water, the high hydroxy group also will act as active sites, maybe assist in the to enhance the performance. So have you considered the role of hydroxy group in this reaction?
Yes, typically when water comes to the surface, you're going to have dissociative adsorption. So water coming, one water molecule, you have one oxygen, two hydrogen. And what happens is that typically on the surface, there will have some oxygen vacancies there. So that actually have affinity to water molecule were sitting on the surface there. That actually help you form a OH group on the surface. And that OH group, as I mentioned in some of the slides there, so that OH group actually also helps adsorption of oxygen. So in the last few slides, I'm talking about the PBCC there. For PBCC, when PBCC exposed to water, the catalytic activity increases or the resistance decreases. I think our preliminary analysis indicate it is because the surface absorption that actually accelerate adsorption of oxygen. Yeah, maybe you can try to see the slides here. That helps the absorption of oxygen, and therefore it actually reduces the polarization resistance. So where is that slides? Okay, this slide here. So this is still preliminary results. So here I have two configuration. This is oxygen absorbed on the, here you have on the top is under dry condition A, and here is under wet condition. So below is under dry. Can you see my? Let me see here. Okay, so this is under dry condition. Okay, under dry condition, this is the configuration, and this is under wet condition. And we're gonna hear what's how the molecule get here. This is configuration wet condition. Those are the frequencies, the vibrational frequency of the surface oxygen species. That has been measured from here, from Raman spectrum. So we can get all the species. This frequency consistent with this is calculate frequency, yeah? The line is calculate, the points is measured. So those are consistent. That means this model is reasonable. And then from that, we can turn around to predict, here's the rate constant for the surface absorption reaction. So here he explains why the PBCC give you lower resistance. Again, this is DFT calculation based on this model here. And what we think is important is because, see here, this PBCC with two vacancies plus water and oxygen, okay, this is wet and this is dry. GBCC with 2 vacancies on the surface plus oxygen. So the energetic, if you forget about the details, just look at the energy landscape. The energy here is higher, and this is much lower. And especially this transition state, the energy barium for the resistance is much smaller. Yeah. So this is just from DFT calculation. Of course, there's a lot of assumptions. It's not necessarily accurate, but it at least give you some good indication. So the conclusion is that because of the presence of water, there's oxygen vacancy, that water come in, fill that vacancy, and that surface structure actually help absorption of oxygen molecule, and the dissociation of oxygen. So if from this spectrum here, you can see this different oxygen species, the peak shift as you change from dry to wet. So from here, we can get some hint about what's going on, and then we put the model together. Basically, this is the explanation. Yeah.
Okay, thank you. And another question from the audience is, now so many questions. Yeah, sorry.
Yeah.
And what's the research directions of the current leakage? Yeah. How to solve this problem? Yeah.
Yes, leakage. Now, first of all, the leakage is due to electronic conduction of the electrolyte. Yeah. Under fuel cell operating condition, because the maximum cell voltage is your open cell voltage. So that is the under ordinary fuel cell operation that is much better than under electrolysis mode. In the electrolysis mode, you are going to impose additional voltage on the cell. Your applied voltage has to exceed the Nernst potential, has to be greater than the Nernst potential. Okay, so that's a most severe condition for the material. And typically, as you increase the cell voltage, you will push the material toward an extreme condition. And that's where you're going to start to introduce electronic conduction. So the most of oxide, when you impose too much voltage, you can calculate the equivalent partial pressure of oxygen. So as you increase the cell voltage, equivalently, if you think about you're changing the chemical condition, the partial pressure of oxygen on one side of the cell will be very low, even lower than in hydrogen. That means one side will be extremely reducing. So you are going to electrochemically reduce your electrolyte. Let's see if you use zirconia. Zirconia is going to reduce from 4+ to 3+, and that's going to create free electrons in the conduction band. That's going to increase electron conduction. In fact, if your voltage is high enough, you can turn zirconia into black. It's called blackened zirconia. You get significant electron conduction. So typically, as you operate the electrolysis cell, as you increase the cell voltage, you have more probability of reducing your electrolyte, and that's going to induce the electronic conduction. So one of the approach is that you want to minimize the overall potential. Yeah. And so there, of course, try to increase the catalytical property for ORR and for other processes will help to some degree. But more importantly, the most important aspect is we may have to come up with a new electrolyte to really sustain the extreme condition, or at least maybe apply a thin film coating of a more stable material, and that will block the electronic transport. So basically, in short, to answer your question is that you need to figure out how to block electronic conduction going through your cell. Okay. when you increase your cell voltage, there's more probability to induce electronic conduction, but you have to figure out how to block that.
Okay, thank you. Another question. Okay, I have to translate. So what's the best way to solve the carbon cork in the reaction in the fuel cell? I think yeah, question
Coking,
like
solve
this.
the
Yeah.
coking problem. Okay, coking. Now, to avoid coking from a chemical equilibrium point of view, if you have higher steam to carbon ratio, and then you're going to reduce the probability of coking, right? So from the thermodynamics, as you increase the steam to carbon ratio, the probability of coking will decrease. So typically you need more water. Okay? So that's why for any hydrocarbon fuel, if I have sufficient amount of water, I can always do reforming. It's not a problem. But from the energy efficiency point of view, you don't want a lot of water because the water is going to dilute fuel, actually make your system less energy efficient. From energy efficient point of view, you don't want to introduce any water. So how are we going to solve that problem? That's where the catalyst become important. So imagine if you have a coating, you have a catalyst on the surface, and that catalyst have strong adsorption of water. Even though the average concentration of water may be only 3%, like you do humidification at room temperature, that's bringing about 3% of water. But if you have a coating, a catalyst that have very hydrophilic, very hydrophilic, so it's absorb a lot of water locally at the surface, the water content is very high. So locally, the steam to carbon ratio is high, then you will no longer have coking. So a lot of the catalysts, the first most important property is it has to absorb a lot of water on the surface. That way, once you can maintain certain concentration or surface coverage of water on the surface of your electrode, then you will be safe. Because as soon as you operate your cell, oxidation of hydrogen produce water. And if you have catalyst there that captures that water, as water produced, you capture that water, use that water to do reforming. Then at the active site for the electrochemical reaction, your steam to carbon ratio is always high. So that will prevent coking. I think basically that's one of the most effective strategies. And you need to locally increase the steam to carbon ratio. So basically you need some catalyst. That's one thing. Another thing is, as I explained in one of the slides, you need some catalyst that specifically promote oxidation of carbon. So like barium oxide. Barium oxide dissociative absorption of water create OH group. The OH group is going to react with carbon to oxidize carbon. So you need a catalyst and that promote dissociative absorption of water, create OH group, and also catalyze the carbon OH reaction, produce COH. And then COH dissociated into hydrogen and CO. Now, hydrogen and CO are fuel for SFC. So hydrogen can be oxidized to water, CO can be oxidized to CO2. So those are the strategies.
Okay, thank you. And what about the stability of CO2 in BGCYYB? Yeah, this is another new question.
Yes.
Thank you.
BGCYYB depends on the composition. For the standard composition 1711, so 1711, then it means you get 10% of zirconia, 7% of ceria, and 10% of yttrium, 10% of ytterbium. Okay, so that's standard composition to high conductivity. That one will be less stable against CO2. It depends on the concentration. If you only have a few percent of CO2, it might be okay. But as you increase concentration, BZCOIB 1711 is no longer stable in CO2, also depends on temperature. And so right now I think we just published one paper in Advanced Functional Materials. We have hafnia and niobium other dopant that can significantly enhance the stability against water and the CO2 for the proton conductors. So you have to tune or tailor the composition of the material to enhance the stability against water and CO2.
Okay, thank you. And I think the last question, sorry, I had to translate.
No
so long.
problem.
Yes, for just now you mentioned in your slides, silver oxide, doped silver oxide, doped with nickel and ruthenium. Yeah, these two elements. So generally speaking, it will sometimes create a vacancy. I'm not sure. Yeah, vacancy. So have you considered the vacancy, the role of vacancy in the reaction for OER
Yes.
and yeah.
Absolutely. Vacancy is critical. Oxygen vacancy is critical for all that processes. Now, silver oxide is well known that is very flexible with oxygen. So you can easily create oxygen vacancies. And if there's oxygen in the atmosphere, silver oxide can take oxygen or release oxygen readily. That's one of the unique properties of silver oxide, and that's why it's so efficient. The silver oxide actually used for a lot of catalysts in a three-way the NOx removal three catalyst. It's also used silver oxide basis. So silver oxide is well known that's going to create a lot of vacancy. When you introduce other like nickel, ruthenium, or other things, that will create additional vacancy. Okay. However, vacancy is not the only thing. If vacancy is the only thing, there are more efficient ways to introduce more vacancy. Yeah. But vacancy is important. Definitely, vacancy play an important role. But in addition to vacancy, you also need nickel cation, ruthenium cation. They're doing other things like breaking the carbon hydrogen bond, breaking the oxygen hydrogen bond. Those catalytic properties, oxygen vacancy is not efficient for those processes. So you need all those work together. You're looking for this synergistic effect. But to answer your question, yes, vacancy is important. But vacancy can be easily created in silver oxide. Vacancy is not the only factor. It's an important factor, but not the only factor.
Okay, Professor Liu, thanks for your detailed response to all questions. And thanks again for your time. And also welcome to submit your work to SmartMed. Yeah, thank you in future.
Okay, sure.
Yeah,
thank you very much.
And
thank you.
Thank you.
好，谢谢刘老师啊，晚安。
Good night. Yeah, good night. So late now. Sorry, so late.
Good night.
Okay, bye.
Thank you.
Okay.
Bye.
Okay, bye.
Bye bye. Thank you.